Welcome to the Thinking Podcast. My name is Geoffrey Wu.
I'm Michael Brandt.
And we're excited to have the famed Dr. Aubrey de Grey, founder of SENS Research Foundation. SENS stands for Strategies for Engineered Negligible Senescence. Essentially, how do we stop and combat the notion of aging? Let's dive right into it. A couple of things I thought, this ideas that I think you were seminal in championing is this notion that aging is not a biological phenomenon really, but a phenomenon of physics. Curious to hear you dive into that and set the groundwork for talking about, our approach here to combat aging.
Sure, yes. Yes, I mean, that actual soundbite, so to speak, is something that I've introduced quite recently, and I've been very gratified that a lot of people have somehow picked up on it. It seems to be resonating with a lot of people, because I think it's really fundamental. The purpose of saying that aging is not a phenomenon of biology, is in order to communicate that aging of living organisms is really, in its fundamentals, very, very, very similar to aging of inanimate objects, in particular of any machine with moving parts, like a car or an aeroplane or whatever. The idea is that because of the nature of the laws of physics, any machine with moving parts, whether or not it's alive, is going to do itself damage as a consequence of its normal operation. Damage is just going to happen. And that damage is going to accumulate in the machine over time as the machine continues to do its normal function. And eventually that's going to be a problem. The machine is set up to tolerate a certain amount of that damage without significant impairment of function. And in the case of living organisms, of course, that means both physical function and mental function, but only a certain amount. Eventually there's too much and the function starts to decline, and eventually the function ceases entirely. So the reason I feel it's very important to communicate that is because people have this misconception in their heads that aging of living organisms is not understood, that it's a mystery, whereas they are perfectly comfortable with the idea that aging of man-made machines is well understood. So I want to explain that actually aging of living organisms is also really pretty well understood. Of course, when it comes to the details, aging of living organisms is much more complicated. There's lots more different types of damage that are accumulating and so on and so forth. But in its fundamentals, the way that we can analyze the phenomenon of aging of living organisms and the way that we can manipulate that phenomenon and make it happen less rapidly or not at all is exactly the same as what we would do to make a car last 100 years when it was only designed to last 10 years.
Yep, I think that's a great analogy because I think that, in our past, I think there's like this bifurcation between living things, animals, humans versus machines. And I think that that distinction is converging. And I think that we're at an interesting point in history where, as we talk about a lot, is that humans are systems, complex systems, but still understandable in terms of inputs and performance outputs. So
I'm actually curious, what's going to happen to the field of biology as we get better and better sensors, better ability to manipulate? Then we're starting to be able to look at things like computer systems or physics systems, things that are a lot more hard science and less like biology can be very observational and like an approach to an organism as a whole rather than like breaking down the exact every single thing like a physicist would. So what's going to happen to biology? Is the approach going to fundamentally shift as we start to think about things at the molecular or physical level?
Okay, I want to give a slightly complicated answer to that question because there are really two dimensions of it that I want to highlight. The first one is that the transition from being descriptive and observational and holistic to being more dissecting, so to speak, to splitting up and analyzing and classifying the components of a system, that is not a single moment. That is obviously a progression that happens as knowledge increases. The other thing I want to emphasize is that we need to make a very clear distinction here between understanding the way that a machine works and manipulating the way that that machine works. The reason that's a very important distinction to make is because the mindset that is involved in coming up with ways to do those two things are very different. If you want to understand a system that you have come across that you didn't build yourself, then the way to do it is to, do experiments and test hypotheses and so on. Whereas if you want to manipulate that system, very often, even though, of course, you are using knowledge that you have about the system that you've gained in that way, what you do in terms of figuring out how to manipulate the system often involves things that a scientist would consider unscientific, essentially leaps of faith that put two and two together and think what would happen. And that does not mean that technology is somehow invalid. It just means it's a different way of going about our behavior than basic science. And the reason I feel it's so important to emphasize all of that is that at the moment it is the main problem with regard to the acceptance by society that aging is a phenomenon that's amenable to medical intervention. What's happened is that aging has only recently made that transition from a phenomenon that has to be studied and understood into being a phenomenon that can be potentially manipulated. And that means that the overwhelming majority of respected, influential experts within the field of the biology of aging are people who are trained to be good basic scientists, to understand phenomena, and they are not trained to be good technologists. So their instincts are generally off base, and their instincts about the potential and the plausibility of particular technological proposals are often very over-pessimistic, and that slows things down a lot.
It reminds me of weather systems where we're able to observe weather systems, but we're not able to engineer or use technology to force a certain climate or subclimate on a consistent basis, where most of our efforts are spent on an observational path.
Yeah, it is rather like that. I mean, of course, we can't yet do much to manipulate the weather, though, of course, that is one of the, if you like, large-scale technological goals of humanity. But we're getting better at predicting it, and the more
I just draw it as an analogy. Yeah.
Yeah. I mean, diving into the controversy. I mean, I think that's something that, I think is an interesting part of your journey as a researcher and a thought leader. I think, there was an interesting 2005-2006 debate with the MIT Tech Review where you debated some of the, premier, ivory tower academics in gerontology.
Most of whom I should point out have now actually come very much on side and very much respect the ideas that I was putting forward back then, even though they didn't understand them very well a decade ago.
Yeah, what do you think was the big difference? It was just that, it takes time for ideas to percolate through.
Yes, I think
people's training. What was the big change?
It's all about time. At the end of the day, it is appropriate for experts to be cautious and careful in their analysis of new ideas, especially new ideas that are profoundly different from what the expert already knew. Because the fact is, most things like that, most heresies, if you like to call them that, are actually wrong, and therefore they are in danger of wasting people's time who are getting on with the serious business of actually taking knowledge forward. But occasionally heresies are right, and when heresies are right, they tend to be very useful indeed. So it's very difficult for any expert, and I include myself here, for any expert to know what to do with a new idea, to know whether to take the time to understand it well and see whether it stands up to scrutiny and whether it can be influential. I think that in the case of SENS, when I first put it forward, there was a lot of difficulty in making that whole argument. And the fundamental reason why there is so much more acceptance of it now is simply because the efforts that were made initially to knock it down and to show that it was unscientific were unsuccessful. It survived the test of time, and the longer an idea survives without being definitively knocked down by anybody, the more likely it is to actually have some substance.
Right. So for the enlightenment of our audience here, SENS, as Aubrey was explaining, is, it basically describes approaches to tackle 7 broad categories of aging or damage, right? And I don't want to bore everyone because this is well reviewed, well talked over all over the internet. But just at a high level, the 7 broad categories are cell loss, cell atrophy. 1, 2, nuclear mutations. 3, mitochondrial mutations. 4, death-resistant cells. 5, extracellular crosslinks. 6, extracellular aggregates, sort of junk outside of the cells, and intracellular aggregates, junk within the cells. After sort of 10, 11 years after you propose the initial framework, what with the recent data do you think are the most tractable out of the 7 that we're on the path to understanding, and what do you think are the most intractable at this point?
So to answer the first of those questions, which is the most tractable, I think the answer is undoubtedly the same as it was when I first put forward these ideas, namely use of stem cell therapy to address cell loss. It was already clear way before I came along that the most obvious and most promising way in principle to restore the number of cells in a tissue that is losing cells progressively over time is to introduce new cells in probably small numbers that will have the capacity, that will be effectively pre-programmed into a state where they will divide and transform into replacements for the cells that the body is not replacing on its own. And stem cell therapy, of course, started a long time before I came along, and it is a burgeoning and very well-funded field. So, in fact, SENS Research Foundation does very little in terms of stem cell therapy, simply because we would be a drop in the ocean, and our very limited funds are going to have more bang for the buck elsewhere. To answer the other end of your question, which are the most intractable areas, those are the things that we work on. Well, I mean, actually, we work on most of the rest of SENS, but certainly the ones that we put the most effort into at this point are the most intractable ones, largely because the ones that are kind of in the middle, that are intractable enough that we have historically focused on them, but which have been yielding to our work and have been making progress, those ones are the ones which have, in the past couple of years, tended to be convertible into private sector enterprises, into spin-outs. That, of course, we have a minor equity stake in, but that are able thereby to obtain financial support from the very large number of people out there who have money and have vision, but who don't like giving money away and are much more keen to actually invest, even if the investment is long-term and high risk. So that's definitely part of our strategy right now, is to spin things out when we can. But the most intractable areas are the ones which haven't got to the point where we can realistically spin them out yet. So, for example, we work on mitochondrial mutations. We have a strategy we're pursuing, which was first devised more than 30 years ago, and which most people gave up on, but which we have revived over the past several years. The strategy involved essentially making modified backup copies of the mitochondrial genes and putting them into the nucleus, into our normal genome, thereby providing an insurance against the inactivation by mutation of the normal mitochondrial copy. This idea is something that we have very recently been able to take to a point that is closer to fruition than anyone else has ever got to before. We actually just had an important paper on this accepted for publication in a top peer-reviewed journal just last week. Another example is cross-linking. So hypertension in the elderly, among other things, is caused by the loss of elasticity of lattice.
Before we dive into that, we actually had a question from a viewer about the mitochondria DNA, and he was referencing in a reading that he read by Nick Lane. And I think, just to give context here, the mitochondria is like the energy, the power plant of our cells, and most of the proteins and most of the genes of the mitochondria have migrated into the nucleus, the nuclear center of the cell, right? And the benefits there is that the nuclear center is much more protected than the mitochondria in terms of mutations, radiation damage, etc.
Right.
But there's still, around 13 genes or proteins that are left in the mitochondria. And my understanding is that, you propose to, how do we bring those backup copies into the nucleus so we can, allotopically express these proteins, basically produce the proteins in the nucleus and then ship them into the mitochondria. So there's less risk of those proteins being damaged in the mitochondria itself. So Jack asks, there's the counter argument to that approach is that there's a reason that these proteins are in the mitochondria, because that each mitochondria can now have its own expression of these protein levels, so you can optimize at the mitochondria level rather at the cellular level. And perhaps the only quote unquote real way to decrease oxidative stress on the mitochondrial DNA is to lower their idle speed, or get them more efficient like birds. Curious to hear your response to Jack's question.
Sure, yeah. It's a very important question precisely because Nick Lane and other people have very much embraced this theory. And so it's quite a popular theory now. It was first put forward by a British botanist named John Allen in the early 1990s. And the idea is, seductive in first hearing. It sounds like it might be a reason why evolution has chosen not to move the rest of the genes, these final 13 genes. But when you look more closely, it's actually very implausible, because there are so many other things that mitochondria already do to regulate their activity that are much easier, less energetically inefficient, and more rapid responses than the approach that this theory suggests, the approach of simply altering the gene expression levels at the level of the individual organelle. It's a very hard theory to actually, to justify in evolutionary terms, let alone in biochemical terms. And so one might ask, well, why has this theory survived? And the reason it has survived is because, of course, the way science works, choosing which hypothesis, whether a hypothesis is plausible, is by ranking it, by comparing it with alternative hypotheses for the same phenomenon. And so here we must not only ask how plausible is the hypothesis that you described, that Nick Lane wrote about, for example. We must also say how plausible is the alternative hypothesis, that it's all about the nature of these proteins being so weird, so what's called hydrophobic, that evolution was simply unable to move them to the nucleus, even though it wanted to, which is the theory that underpins the approach that we're taking. Now, when John Allen first looked at this question, perhaps he was handicapped by the fact that he was mainly looking at plants, because he's a botanist. But anyway, one way or another, he came to the conclusion that there were quite a lot of really, really severe counterexamples to the hydrophobicity hypothesis, to the idea that simply evolution wanted to do this, but it couldn't. And he pointed out some counterexamples. And he felt that, well, yeah, okay, maybe there are arguments that say that this alternative hypothesis about gene expression in the organelle is also pretty implausible, but at least it doesn't have counterexamples. And that's a reasonable argument. But it's only reasonable if those counterexamples really are counterexamples. And it turns out they're not. It turns out that the hydrophobicity hypothesis is not actually challenged by any of the so-called counterexamples that were put forward. Now, in order to explain why that's true, I would have to carry on speaking for another half hour. And so I won't do that. What I will do instead is just mention that more than a decade ago, around 2005, I wrote a long and very painstaking review of all of these so-called counterexamples that was published in a journal called Bioessays. Anyone can write to me and get a copy of that paper if they want, in which I very carefully analyze each of these cases and showed that actually it's perfectly consistent with the hydrophobicity hypothesis. So what this leads me to believe is that actually that hypothesis is far more consistent with all the evidence that we have than the alternative that Nick Lane put forward.
Great. Yeah. I mean, I think that this is what science is about, right? Like debating ideas and seeing what evidence holds up. I hopefully Jack, we'll have you send that paper over to Jack to help
sure.
Educate him there. I'm curious. You were talking about crosslinking before I interrupted you with that question.
Sure. Okay. So that's another of the really difficult areas of SENS. The phenomenon that we are interested in combating is the accumulation of chemical crosslinks between proteins in the spaces between cells. And here these proteins that I'm talking about are not the ones that are accumulating as waste products in aggregates. I'm talking about ones that actually have an important function. These proteins make up a kind of lattice called the extracellular matrix. And that matrix is what gives our tissues their physical properties, in particular elasticity. Now, elasticity is really, really important for some of our tissues. Like, for example, the lens of the eye. It has to be elastic in order to be able to be deformed so that we can focus on things that are close up. Similarly, our skin needs to be elastic in order not to wrinkle. But the most life-threatening example of this phenomenon is the major arteries, which need to be elastic in order to essentially buffer our blood pressure against the constant pulsation from the heart. That buffering is essential in order to minimize damage to the more fragile, small blood vessels, the capillaries, that are further downstream, away from the heart. And as time goes on over life, we accumulate these crosslinks in the extracellular matrix. That makes the major arteries less elastic, more stiff, and thereby it increases blood pressure. It means that the heart has to do more work, and it also means that the capillaries are more vulnerable to damage. So it's very, very important that we figure out a way to restore the elasticity of these various tissues, especially the major arteries. And the way to do that, the natural way to do that, is just to find chemicals or other means to break these unwanted accumulating crosslinks. All right, so originally, when I started contemplating the idea of SENS back in 2000, this didn't seem to be too severe a problem. Papers have been published over the previous few years that indicated that there was a lot of potential for identifying chemicals that could indeed break these crosslinks and would not have significant side effects. The avoidance of side effects looked as though it was going to be pretty easy because actually the chemical structure of these spontaneous, unwanted crosslinks is very different from the chemical structure of anything that the body lays down on purpose. So the specificity wasn't really an issue. However, it turned out that the positive attitude, the positive opinion that scientists in this area had back in the late 1990s was misplaced, that it was over-optimistic. And around that time, people began to identify additional cross-link species, additional chemical structures, which were not amenable to being broken by these chemicals, and indeed were not obviously amenable to being broken by any chemical. And unfortunately, those other crosslinks were accumulating more rapidly than the ones that seemed to be easy to break. So in other words, the main problem, the core of the problem, was not amenable to intervention at that time. And unfortunately, that's pretty much where things stay. Very much in the same way that people more or less gave up on allotopic expression as an approach to alleviate mitochondrial mutations. Similarly, people decided that it was just too hard to break these crosslinks. And so the emphasis of research shifted very strongly into looking for ways to stop the crosslinks from being created in the first place, which of course has some value, but it's not much use for people who've already got a lot of crosslinks. So we picked up this baton, as we tend to do, and we tried to have a go at it. And eventually we got very lucky. We were able to connect with a fantastic research group at Yale University in New Haven, which is led by a guy named Professor David Spiegel. And that group was able to make real headway here. The first thing that they had to do, which sounds a bit paradoxical when I first say it, but it's very important, is to actually create these crosslinks, not to break them, but to make them. But to make them not in the body, the way that they naturally accumulate, but rather to make them in the test tube. The thing about these crosslinks in the body is that it's very, very hard to work with them because they aren't all that abundant, and they can't be isolated without a lot of very laborious work carefully breaking down the proteins that they are linking between without breaking the links themselves. So this was just completely impractical. And the result was that one couldn't develop assays. One couldn't even raise antibodies against this stuff, let alone identify chemicals or enzymes that would break them down. Now that's all changed. As of a couple of years ago, this group that we've been funding were able to develop a very cheap and very efficient way to synthesize large amounts of the main crosslink that matters, something called glucosapane, from simple, cheap starting materials. That was published in Science, the #1 scientific journal in the world, just about less than a year ago. And since then, that group has been, of course, beavering on at a pretty fast rate, trying to identify ways to break this stuff. So we have essentially completely unlocked a 20-year logjam that existed in this whole field.
That's very cool. I mean, I think it's heartening to see some of the long work of going through the doubters to start panning through to actual potential therapeutics or approaches here, which is
Thank
cool. I want to dive into intermittent fasting and caloric restriction.
Sure.
It's something that a lot of our community is interested in. Both Michael and I personally do 36-hour fasts weekly. I think the data around uh, you know, improving biomarkers in terms of insulin resistance, blood pressure, uh, boosting certain things like BDNF to accelerate adult neurogenesis is pretty compelling.
Yep.
Curious to hear your thoughts on this because you know from a lot of your literature, I think the data on health benefits or performance benefits is fairly clear, but I think it's a little bit I would say controversial on lifespan extension, which is more of your wheelhouse. Curious to hear your thoughts there.
Sure. All right. So first of all, I want to say that I do agree that a lot of people, maybe even most people, do have the potential to derive some benefit in terms of health from this kind of dietary manipulation. Call it calorie restriction, intermittent fasting, whatever. I don't think we really need to get into the distinctions between these various flavors of the method because they all really have the same result. Some people almost certainly can't get any benefit. I, for example, I have perfect glucose metabolism and insulin sensitivity, despite the fact that I have pretty much undetectable levels of insulin. So that
You eat very
really
little. I mean, you're
I,
you're a thin guy.
I eat and drink exactly as much as I feel like. I
Okay.
don't choose to eat less or drink less. So, some people are just lucky like me. People who are the luckiest, naturally, of course, are the people who have the least to gain from doing this kind of thing. So I don't think it makes much sense for someone like myself to engage in calorie restriction. However, I do agree with what you said, that for most people who are not so lucky already as I am, there is some logic to it. So then the question is, what is the limit to that? What can't calorie restriction do? And you mentioned lifespan. I want to step back a little bit because I always want to make sure everybody understands that we don't really work on lifespan. We don't work on longevity. We only work on health. Any kind of benefit from our work that can be measured in terms of increased longevity is purely a side effect of the improved health and the postponement of ill health. So then the question is, what do we think of calorie restriction and its friends in that regard? And I've just said that I think that there can be a significant improvement of health. So you might well think that actually must translate into a significant increase in lifespan. But it turns out that's not true. It turns out that perhaps because there are some aspects of ill health that are perhaps not very well measured, but the calorie restriction does not significantly alter, calorie restriction doesn't work very well in long-lived organisms by any measure that we do have in terms of health and in terms of longevity. What we see is a very steep inverse correlation between the natural lifespan of a species and the proportion by which that lifespan can be extended using calorie restriction. In worms, nematode worms, which normally live about 3 weeks, we can increase the longevity by a factor of 4 or 5, or perhaps even more, by that kind of approach. In rodents, rats or mice, we can get 30-40%, but we certainly can't get a factor of 4 or 5. In dogs, it's been done once very thoroughly, and the result was about 10%. In monkeys, it's been done twice, extremely thoroughly, at great expense, and the result of the two experiments was somewhat divergent. One experiment basically got nothing, and the other experiment got maybe 5%. The truth is probably somewhere in between because in retrospect, one can look at the diets given to the control animals that were not being calorie restricted, and one can see that in one case maybe they were being slightly calorie restricted, whereas in the other case maybe they were being a bit poisoned. So the truth is probably halfway between.
Right. So, I would also say that there's also some arguments that they were locked in cages, so there's some, mental, stress there that wasn't properly, doesn't reflect, true, base reality.
That's true, but of course the control animals and the treated animals were both locked in cages. So one has to work quite hard to make an argument from that says